So I'm happy to introduce Isabelle Charton from the University of Haifa, and she will talk about the equivariant cohomology of Hamiltonian T-spaces of complexity 1.
Sorry, can the speaker unmute herself?
It is now better? Yes. Perfectly, yes. Okay, let's start. I'm going mainly to talk about results which are mainly with Liat and also with Nicholas. And let me start with ideas, or better with a notation. So in my talk, Hamiltonian T-space will be always like a compact symplectic manifold. So I will always assume that the manifold is compact and also connected. And we're assuming that we have a effectively and Hamiltonian action, and the action comes with a moment map. The complexity of the action is the integer k and minus the complexity of d, and we call such a quadruple a complexity k space. Or whenever I'm not referring to the complexity, I will say like a Hamiltonian T space. So, but this is the notation. And ideas. So Charton has classified complexity 1 spaces by their so-called decorated graphs. And we would like to extend the definition of decorated graphs to complexity 1 spaces of higher dimension. And ideas. So for a Hamiltonian T-space, it's one skeleton are the points in the manifold whose orbit has at most dimension 1. And for the case that we have like a complexity 1 space, then loosely speaking, we can think about the one skeleton as a union of complexity 0, 2 spheres or 4-dimensional complexity 1 spaces. And in particular, in dimension 1, in dimension 4, complexity 1, we have that the one skeleton is M itself. Okay. In dimension greater than 6, we can still store the information of the one skeleton of a complexity 1 space in a graph. And we also call this the decorated graph. And now I would like to go over how we define the decorated graph, or what is the meaning of the decorated graph. As with Liat, it's still a process in work. We have the following. Let be a complexity 1 space in dimension greater than 6. Then its decorated graph determines the equivariant cohomology ring and the equivariant Charton classes, and also the ordinary cohomology ring and ordinary Charton classes. And a very nice special feature is when you are in dimension 6 and you're assuming that the underlying manifold is simply connected, then the decorated graph also determines the diffeomorphism type. And so now I would like to explain what is the decorated graph. Namely, whenever we have like a complexity 1 space, and whenever we have a connected component of the fixed point set, then it's really easy to show that X is either an isolated fixed point or a compact surface. Okay, and so it's really like similar to its definition. We now define what are the vertices of the decorated graph. Namely, the vertices are the connected components of the fixed point set. We label each vertex by its moment map image. And so, as I told you before, a connected component of the fixed point set is either a fixed point, is either an isolated fixed point or a compact surface. And in the case that is a fixed surface, the vertex is called fat, and it's additionally labeled by the genus and the symplectic volume of the underlying fixed surface. Okay. And I would like to recall Charton's definition for the edges of the decorated graph. So let us start. So we are assuming that we have like a 4-dimensional complexity 1 space. then the fact is that for an integer greater than k, the closure of the connected compound, so you consider points whose stabilizer are not trivial but by a finite group, then this closure of any such a connected component is a two-sphere. And when you have such a two-sphere, then as the closure intersected with the fixed point set is the union of two fixed points, and these are isolated fixed points. And if whenever there exists such an edge, then there exists an edge between P and Q that is labeled by K. Okay. And yeah, here for example, I'm going to remind you on an example. So we're starting with a toric image. So you have maybe here this as one action. So in this case, you get the decorated graph as the following. You have one fat vertex and one small vertex. The genus of this creature is 2, and omega is 3, 2. Or for example, you can also do it for example, on CP2 and CP1 cross CP1, and you take a surface like this, then you get a decorated graph of 4 isolated fixed points and 2 edges which are both labeled by 2. Okay. And let me remind of this wonderful work by Yael, because she classified the the four-dimensional complexity 1 spaces, and namely, whenever we have 2 four-dimensional complexity 1 spaces, then any isomorphism between the corresponding decorated graphs is induced by an equivariant symplectomorphism. Okay, and I don't want to go into the details, but how do we define the decorated graphs in high dimension? And here I would like to start with an example in dimension 6, which is coming from a toric creature. So how to say, you start, for example, with CP1, CP3, and you take the subtorus like this. And what you get, what's the one skeleton of this creature? Now, I mean, how to say, these 2 facets here, they will collapse to a 4-dimensional edge in this 2-dimensional picture. So you get a 2 surface here, which is coming from this edge. And additionally, you have to remind the information about the surface, which is here. And so we remind this, and so you get the decorated graph in dimension 6. Another example would be I'm sorry, I'm feeling cheating because taking the example. So you take an example like this, and you consider the following subtorus. So in this case, there's one edge which clubs to something 4-dimensional creature, and so you get the following decorated graph. And here, I'm a little bit sorry because to make it clear, the edge is a little bit curved. But here we have 4 isolated fixed points and an edge here. And yeah, so this is the idea behind the decorated graphs. And
oh, sorry, so let's say you're in the circle action thing, you have this 73. Do you draw those edges of weight 1 in that case still? Or?
Actually not.
So it's not extended decorated graph?
Yeah, it's so loosely speaking, we are how to say, summing up in 4-dimensional creatures of Yael's graph, and then we're adding 4-dimensional pictures. And I would also like to give an application in dimension 6 for the monotone case. And therefore, I would like to recall a definition. A symplectic manifold is monotone whenever the first Chern class is a multiple of the class given by the symplectic form. And there are many different definitions in literature, but here I would say monotone, I'm still assuming that this lambda is greater than 0, but however, this is some kind of okay. And important examples of these monotone creatures are the so-called smooth funnel varieties. So they're very important. And then a classification result which I have made with Liat, and it's in work in progress. And namely, we showed that whenever you have like a 6-dimensional monotone complexity 1 space with only isolated fixed points, then its decorated graph is isomorphic to a smooth funnel variety endowed with a holomorphic action. And how we did prove this result. So the result for the case M is made by a computer program. And the algorithm on this is based on a work by Leonore and Cadinho. But we cannot use the algorithm perfectly. We have to modify it a little bit. So, because if you just run the algorithm here, you will end up with fake creatures, and we use some kind of like homology properties to rule out these fake creatures. Okay, and yeah, so then Nicholas, so he did the following. So he was like classifying for the following case, 6-dimensional the decorated graph of 6-dimensional monotone complexity 1 space whenever you have like that this fixed point is not isolated. And from his work, we also have that the corresponding decorated graph is isomorphic to the one of a smooth funnel variety. And so, but the proof here is very different because for the isolated fixed points, we really need a computer algorithm to solve it. And here you can do it somehow by hand, but it's not trivial, but you can do it by hand. And so, therefore, we obtain the following theorem, namely that whenever you have a monotone complexity 1 space of dimension 6, then we have that the underlying manifold is diffeomorphic to a smooth funnel variety. And yeah, and some kind, we have the following conjecture, namely whenever we have like a complexity monotone complexity 1 space of dimension 6, we are assuming that this space is equivariant symplectomorphic to a smooth funnel variety endowed with a holomorphic T action. And why we do assume this? We are assuming this because actually I was hiding some things, namely, so far everything looks like this, and I think with Liat, Nicholas, and also and Sue, I think we would like to prove this conjecture because it's like extending the classification you have made for complexity 1 for the non-Tau case. Okay, then yeah, this is actually what I would like to say. Then I have a lot of time still left, but yeah, so thank you for your extension.